Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss about estimation of errors in measurements of properties in MD simulations. So, like in experiments, when we measure certain quantities, there are often several sources of errors. So, in MD simulations too, such errors emerge. So, we need to measure such errors whenever we report any thermodynamic or transport properties that we measured from simulations. So, you might see this kind of fluctuations in several variables. For instance, what we are showing here is this energy as a function of time in a typical MD simulations. So, initially there is a drift, and then if you wait long enough, we see that this quantity, in this case the kinetic energy, fluctuates about a mean value. And in fact, we said that such a characteristic is coming from the equilibration phase. If you look at the potential energy also, you can see that this potential energy fluctuates about a mean value, and similarly the pressure also. So, whenever we see this kind of a steady fluctuation without any drift, we identify such a phase as a equilibrated phase, and from here onwards we can start measuring properties. The properties that we are interested in could be a simple equilibrium averages, or it could be a fluctuation based measurements, or it could be even time correlation based measurements. So, regardless of which property we want to measure in MD simulations, we often find that any such measurements show fluctuations about a mean value. So, that is a very characteristic of a MD simulation result. Now, the question you would like to ask is, what is the magnitude of these fluctuations and what is the nature of such fluctuations? So, that is the context of this particular lecture. So, before we go further in calculating errors in MD simulation results, first let's ask a question that what is the nature of these fluctuations and what kind of distribution these fluctuations have about. So, I am going to show a simple derivation that demonstrates that any property that we measure in MD simulation, thermodynamic property, under true equilibrium conditions will have a Gaussian distribution. That means it will have a mean value, and then there is going to be a standard deviation. And the reason why we say it is a Gaussian variable is because if you look at the material we presented in statistical mechanics, we can easily show that. For example, in this example, I am taking an NVA ensemble. Okay, that means the number of particles is fixed, volume is also fixed, so the density is fixed, and then the total energy is also fixed. So, it is basically an isolated system. And we noted that for an isolated system, the thermodynamic potential is entropy, and it is given as Boltzmann times ln of omega. So, this omega here is the number of microstates. Sometimes we would have written this as QNVE as a partition function also. Okay. So, in the case of NVE ensemble, the partition function and the number of microstates omega are the same. Now, with this definition, if I know the number of microstates omega here, then we can derive all the thermodynamic properties of the system. And if I am interested in any particular quantity A, this A can be a kinetic energy, or can be a potential energy, or it could be a pressure, or any property that we want to measure could be written as an ensemble average, which is basically the integral of the property A times the probability of finding a microstate at the same property A, and then you integrate over all possible A values. So, this gives an average estimate for a property A. Now, this probability P of A is basically the probability distribution function that says among all the microstates that are possible, how many microstates are there in which the property A has a particular value A prime, and it is given by the ratio of the microstates. These are the set of microstates where the property A is equal to A prime, and this omega is the total, all the possible microstates. It is basically a fraction that tells what is the probability. So, now we can write this omega in terms of the corresponding entropy. So, this entropy is not the full entropy, it is only the entropy corresponding to all the microstates in which the property A is at a value of A prime, whereas this omega here is going to be the total number of all the microstates. So, now if I have an expression for this entropy, then I can substitute here and get a value for expression for the probability, and it can be substituted here to get the mean value of A. To see that, what we are going to do is we are going to expand the expression for entropy about a value of entropy corresponding to the mean value of A. So, what we are saying is this property A has a distribution, it can vary, it is fluctuating quantity, but we know the most probable value for A is this given by this mean value. Justification for that is by looking at this kind of graph where there is a fluctuation. So, that means the value is changing, but then the mean value is something we can observe from this particular data. So, we would like to basically expand the entropy about a entropy corresponding to the mean value of A, and then we take the first derivative times delta A, second derivative delta A square, and then higher order terms. So, you will have these terms which we have neglected. So, it is a simple Taylor series expansion, and all these derivatives, the first derivative of S with respect to A, S with respect to dou square S by dou A square, all of them are estimated at this particular reference position, which is the mean value of A. And we know that when the system is at equilibrium, this S has to be maximum value. Okay, that's the definition for equilibration or equilibrium condition. So, that means when A is equal to mean value of A, the first derivative goes to 0 because the entropy is maximum, and the second derivative must be negative. So, this negative we write with certain parameter minus C K B. So, here C is a positive constant, K B is Boltzmann constant, they both are positive. So, that is why we put a negative sign here, so that the second derivative is negative. So, that the entropy goes through maximum at A is equal to A mean A value. So, if I plot, we are expecting something like this, entropy goes through some sort of a maximum value at mean. So, at this particular position, the first derivative vanishes, second derivative is negative, and then that second derivative we are writing is with some unknown parameter C that basically shows what is the curvature of this function. And then we take this expression, and the first term is the entropy corresponding to the mean value of A, the second term vanishes, and the third term basically survives, and then we write the second derivative as minus C K B by 2 S minus S A whole square. So, you can see that by expanding the entropic expression, we are approximating the curvature locally here to a parabola like this. So, now we have this entropy, we can go and then substitute in the expression for the probability function for a particular value of A. So, here this omega is written as exponential of the entropy, that is because we know that S is equal to K B times ln omega. So, from here omega is nothing but exponential of S by K B, and then we keep this omega as such. So, now we have got this expansion through Taylor series expansion, and we are going to substitute that in this expression. So, when you do that, you can see that there is going to be two exponential function, one that is exponential of S at mean value of A divided by K B, and then multiplied by exponential of the second term, which is minus C by 2 A minus A whole square. So, you can see this K B gets cancelled because of this factor here. So, now we also have to take the property of this property function, that is when I integrate this P of A over all possible A, this should be equal to 1, that is the definition for a probability function anyway. And then using this particular identity, we can find the prefactors of this particular expression. So, you can see that these terms are basically constants, they will come out, and then only this particular function has to be integrated out. And then when you do that, you can show that this exponential of S by K B by omega times square root of 2 by C becomes equal to 1. So, now we can take this expression and then substitute here, and then show that this P of A, that is the probability that a particular value of A will be observed, is basically given by a Gaussian random variable with a mean value of mean A and the variance sigma square given by 1 by C. Okay. So, this basically we are writing based on the matching the terms in a Gaussian random variable. And the interesting thing about this particular distribution is that if I look at the relative error, that is the standard deviation divided by the mean value, you will see that that goes as 1 by square root of n. That is because this fluctuation sigma square is of the order of n, and this mean A can be of the order of n. If this is an extensive quantity, then the sigma will be proportional to square root of n, and then this is proportional to n. So, you get 1 by square root of n dependence. So, what this basically means is that this relative values of this error or the standard deviation will decrease proportional to 1 by square root of n. So, larger the system size, lesser will be the fluctuation. This is something you can relate to some of the discussion we had in the previous classes, where we looked at the fluctuation in internal energy for two system size 108 particles and then 500 particles. And then you can see the amount of fluctuation in the small system is quite big, whereas if you look at the larger system size of 500 particles, you see that the fluctuation comes down, and that effect is what we see here, because it goes as 1 by square root of n. And this also tells us that if I have a experimental system or thermodynamically large system where n will be of the order of Avogadro number, then you will see as if this A is not a fluctuating quantity, but it is simply like a mean value with close to 0 fluctuation. That is because 1 by square root of n will be negligibly small, and we think of it as a deterministic variable with single unique value. But then in MD simulation, we often work with a very less number of molecules, less number of particles. Then the fluctuation becomes dependent on the size of the system. So we have to look at the system size dependence on the fluctuations as this. So the main result that we want to show is going back here, that in an MD simulation, we choose a particular system size, and then we see that at equilibrium, the properties that we measure has a particular fluctuation, and this fluctuation is about a mean value, and we can always find the average value from that data. But then to quantify the fluctuations or the error in the estimate, we need to know what is the nature of the fluctuation, and then from a simple thermodynamic derivation, we show that the fluctuation should be a Gaussian random variable, and the fluctuation basically goes as 1 by square root of n. So larger the system size, lesser will be the fluctuations. So we will keep this in mind, because later on when we discuss about the meaning of the error bar, the meaning of the statistical error, we have to always think about the random the property that we measure has a error that is Gaussian random variable. So with that, now we ask, in MD simulation, what are the nature of the errors that are coming up? In principle, there are two kinds of error we talk about. One is a systematic error, the other one is a statistical error. So systematic errors refers to certain parameters that we specify in conducting simulations. It could be what is the number of particles we have used, and some of the ways in which we create random number generator. In certain process, we need random numbers to do MD simulations or even MC simulations. So those random number generator could also have a systematic error. Sometimes our equilibration is not proper, so we have a very poorly equilibrated system, and then we might have systematic error from there. Sometimes we choose a delta time step, sometimes we choose a particular integrator. So all these decisions of system size, the simulation methods, parameter choices, cutoffs, so all these will lead to what is called a systematic error. So now in any simulation, we have to minimize the systematic error as much as possible, and we can take care of the systematic error by doing many checks. For example, in the case of a system size dependence, we can always do simulation with slightly larger systems and then see how sensitive the results are with respect to the system size. Similarly, for the random number generator, you can use different kinds of random number generator and see how sensitive the results are to the random number generators. Similarly, for the equilibration, we can try to simulate the system with the different initial conditions, making sure that the system is really in equilibrium and not stuck in any particular metastable states. During the lecture on equilibration, we already discussed a few methods by which we can verify whether the system has reached equilibrium or not. And then similarly, time step also is something we can always check. We can decrease the time step by 2 times or 5 times, and then look at whether there is any systematic dependence on the results due to the time step effects. So all these things are possible for us to test the effect of any of these system parameters in the measured quantities. So it's very easy to handle such systematic error. However, there are other sets of error which are known as statistical errors, and these comes about because I showed in that derivation that any property that you measure in simulations or any thermodynamic property of a finite size system will have a Gaussian distribution of values, but that is only under truly equilibrated system. But in actual simulation, MD simulations, we conduct the simulation, we make sure the system is equilibrated, and after that we record certain simulation data over a period of time, and then we measure quantities during those production runs. Now sometimes the measured quantity can be a function of how long or how many data points we have averaged over. So, the statistical error mainly comes from such a finite simulation length over which the properties are measured. So, you want to look at that particular aspect in more detail and how to measure statistical error in MD simulations. And these are important because when we report a value from simulation, as I said, just like how we report error bars in experimental measurements, the same kind of error bars are required in simulation data also. Without a uncertainty or error estimate in MD simulation results, we cannot be very confident about what the number says from your MD simulations. So, it is very important for us to understand the calculation of statistical errors as well as eliminating systematic error. All these errors will have consequence on our decision about what is the statistical significance of the results that we report from MD simulations. So, let me go through this methods by which we calculate properties. So, now when we talk about property measurements, we have to remember that we have ensured the system has reached equilibrium, and after that decision is being made, then we run the simulation for a little longer, during which we either do calculation of properties on the fly, or sometime we write the data set in a file, and then after the simulation is over, we can read the data from the file and then do post processing to make measurements. So, now we are looking, so that we have to always keep in mind that the equilibration step is already done, we are talking about only the production step. So, typically what we do is, in the production run, we run a simulation and then we record the data, raw data, which could be a particle coordinates, it could be particle velocities or forces, or any of those atomic property can be stored for about, let us say, some tau run steps. This tau run steps is basically the number of steps at which we have stored the simulation results. And for example, if you want to know what is the run average, so the run average is nothing but the time average, because it's MD simulations, we have recorded data as a function of time, and then when we average over these times, we are talking about time average, which is also known as running average or run average of certain property A, and we denote this with an angular bracket so that it is an average, and this suffix run basically means it's a time average in an MD simulation. And the way you would do that is, you go to each of those simulation data from first to some tau run steps. Okay, so it's basically like this. After equilibration, you write the data at point 1 and point 2 and point 3, etc. You have some tau run number of data points that you have stored, and the time interval is something that you would have defined already based on your frequency at which you want to write these data points. These need not be at every time step. It may be written after once in 10 time steps or once in 5 time steps, etc. So, now if you have this discrete set of properties, and then we sum all these properties and then average over the total number of run steps. Okay, this is a simple arithmetic average of the property A. And then if each quantity A of t here is statistically independent, then we can calculate variance in the mean. So, now suppose if all these data points stored at these discrete time intervals, if all of them are statistically independent, then we can calculate variance in the mean sigma square as sigma square A by tau run, where the sigma square A here is nothing but the variance over the entire set of data. Okay, you can see that this kind of a definition for variance calculation in statistics and probability theory courses. Now, what do we mean by statistically independent? It means that all these data points do not have any correlation with themselves. That means each data point do not have any memory of the previous set of data points. So, they all have independence independently gathered. If you write the data set very closely spaced, then you will see that there will be some memory effect, there will be some correlation between the data set. So, here suppose if you assume that if all these data points are statistically independent, then the formula to calculate the variance in A is by standard formula. But if you want to know what is the variance in the mean that we calculated, that means what is the variability in the estimate of mean itself, so that is given by variance of A divided by the total number of steps with which we have calculated this means. So, now once we have this sigma square A mean A run, and if I take the square root of that, that basically gives me the estimated statistical error in the mean value. So, calculation of average or mean value is straightforward. Now we ask the question, what is the estimated error in the mean, that is given as sigma of mean A, and that is given by the variance of A divided by the total number of simulation runs or the data sets with which we have averaged. And once we have the sigma, we generally report the measured value of property A in a simulation would be the mean value obtained from here plus or minus the sigma. This sigma is basically gives us what is the confidence or what is the error in the estimate of this mean value A. Now the question is, how do we calculate this A? We can do this, we can use this formula provided that all these data points here are statistically independent. Now the question is, we do not know a priori whether the frequency with which we have stored the data set in the MD simulation are statistically independent or not. We do not know a priori. Suppose if there is some correlation and there is some statistical dependence, that means we have written the data set too frequently so that there is always some dependence on the data set. Then what we would have done with this formula is that we would have actually underestimated the error, because not all these number of data sets are statistically independent, only some of them are. So let's say only half of them are statistically independent. So since we are dividing this sigma square by tau n, we are actually going to be underestimating the error. Okay, so that is going to lead to a erroneous calculation of error itself. So we need to know, out of this tau n data set, how many of them are actually statistically independent. Then we can correct this particular divisor, and then a correct estimate of the error in the mean can be calculated. So in order to see that what is the level with which this data set are correlated, we have to look at the correlation time of the properties. You may recollect that we have looked at correlation function CAA defined as the autocorrelation function of A is defined by this expression, and if you plot, you will see that this correlation function is highly correlated at time t equal to 0, delay time equal to 0, and then when you go to very long time, it basically goes to 0. So this basically tells pretty much what is the amount of time with which the data sets are correlated. So we are talking about for a particular property A here. This A can be here velocity, it could be energy, etc. So now what we want to do is, based on this kind of a time correlation function or autocorrelation function, we would like to define a correlation time which is given as integral of CAA from minus infinity to plus infinity C of t, that basically area under this curve. You can see the CAA is actually a non-dimensional quantity because it is a normalized. So the integral will be a time, it will be in the units of time, and we designate that as a correlation time. So if I have a function that has a very quick decay, so this will have a smaller correlation time, whereas this one will have longer correlation time. If you have a curve something like this, it will have even larger. So you can see by area under the curve here is basically given by correlation time. That gives us an estimate of how much the data are correlated among themselves. So then in the actual data set that we have not taken care of this correlation time while printing the data. We may not have known that the correlation time. So we would have arbitrarily fixed a certain interval with which we would have written the data set. So now going back to this particular number of data sets, and we see that the A of t value that we have stored, they are basically separate, they are basically statistically independent only after tau c time steps. Suppose if tau z becomes like 1 picosecond. So data set that are separated by 1 picosecond only are statistically unrelated, whereas data set which are closer than or shorter than 1 picosecond will be highly correlated. So then we have to find out what is the effective number of data sets that are statistically unrelated, could be given by the total number of data sets divided by the correlation time tau c. So just like how, so this will give us, even though you might have 1000 data points, but if the correlation time itself is 10 data points, then the effective number of data sets we will have will be 1000 by 10, which will be 100. Only 100 data points there, all of this 1000 are nearly uncorrelated. So we make this correction in this equation. So we redefine this, the variance in the mean as sigma square by tau prime. So this is basically the number of uncorrelated or unrelated, statistically uncorrelated data sets, and we substitute for tau prime as tau run by tau c. This is the total number of data sets we have, and this is the correlation time. So this will give us the correct estimation of error, because we have taken care of the actual number of data set that are statistically independent, whereas in this expression we assumed that all the data point could be correlated. So now based on this kind of autocorrelation time calculation, we can find what is the autocorrelation time, and based on that we can calculate or correct the estimate of error. So now if I want to use this equation, it means I can calculate sigma square A from the data set. Tau n is also known to me, but what I do not know a priori is this correlation time. I do not know what is the length of the correlation for a given property A. So to go forward, we need to find out what is this correlation time. For this we can do two approaches. One approach is we can do an independent simulation and then calculate this kind of a correlation function for A, and then calculate tau c by integrating the normalized autocorrelation function. So that will give us what is tau c for a given property of interest. Okay, so before we actually calculate measurements in MD simulations, we do a short simulation and find out what is the actual correlation time, and then use that in this expression. So as you can see in the production run, what we can do is we can store simulation data at an interval of tau c. Now we know now we have calculated correlation time. So when we record the data set during the production run, we don't arbitrarily record the data, but we record the data only once in tau c time steps, so that we know, we are sure that each data set that we print or store are statistically independent. Then if you have such number of data sets which are statistically independent, then we can use the standard formula to calculate the error in the mean. So this is one approach. So what we are trying to say is that before you run your production run, you do a short simulation and find out what is the correlation time by calculating autocorrelation time and integrating it out. After that, in the production run, you record or store the simulation data only during once in tau c number of time steps, so that we guarantee that all these data sets are statistically independent, and then we can straight away use this expression to get the error in the mean. That's one approach. The other approach is we might have this simulation data set at arbitrary interval without taking regard to the correlation time. For example, we could have stored at every time step, or once in every 3 steps, or once in every 5 step, etc. Now we would like to calculate the correlation time within this data itself without really doing an independent simulation to calculate correlation time. So now we are going to pay some attention to this method too, because in most of the times we do simulation and record data and then we do post processing. So knowing a priori is a good thing, but generally it is not practiced. So now we are looking at a situation where the simulation is over and we have printed the data at certain interval, arbitrary interval, and how can we make sure that the data set is, how can we measure error in the mean from this data set itself? That's what we are going to discuss now. So now the way we do that is we are going to basically take this data set and then make blocks of various lengths. Okay, so for example, so now we are talking about data set which may not contain all the data set which may not contain all the data as statistically independent. So there could be some correlation between the data sets. So now what we are going to do is, first we define a length of the data set. So that means we take each point and then consider them as one block. Okay, these are subsequent data sets. Okay, and then you can see that, and I consider each of these data sets one block, then I'll have tau n number of blocks. In the second step, what I'm going to do is I'll combine these two and then I take that as one block. So that is, data 1 and 2 consist of the first block, 3 and 4 consist of the second block, 5 and 6 consist of the third block, etc. And then in the, so by this, the number of blocks would be tau n by 2, because I have combined 2 data sets into one blocks. So the number of such blocks or number of such segments would be tau n by 2. The next thing is I can take 3 data sets, that is 1, 2, 3, I make them as one block, and then 4, 5, 6 as another block, 7, 8, 9 as another block. So now we can see that the number of such blocks would be tau n by 3, and then you can extend this approach by making the length of this segment longer and longer. For example, in this case we have chosen tau b, this is the tau b, that is the length of the segment, and then the number of blocks here would be given by tau n by tau b. Okay, and then if you continue to do this operation, what will happen is finally we will have just one single block having this length equal to tau b. So what we are trying to do is the same simulation data we have printed in a tape, So we are trying to make them into various blocks of various lengths. And since the total data set is constant, number of data points constant, based on the grouping and based on the length of this segments, the number of such blocks will also change. You can see the number of blocks will be highest here and the number of blocks goes to 1 here. Whereas tau b, the length of the segment is 1 here, and here it goes all the way up to tau run. So we are able to make such blocks. The reason why we do that is, if I look at this kind of blocking operation, if I calculate mean from any of this blocking operation, the mean will not change, the arithmetic mean. However, by combining data sets into small blocks and then taking variance from these blocks, we can actually reduce the statistical dependence of the data set. So this blocking operation basically allows us to decouple the statistical dependence among the data sets. For example, if you consider these two data sets, they could be highly correlated because they are separated by a 1 unit of time step. Whereas if I look at this particular segment and this particular segment, and I can average a value of these three, and then I can average the value of these three, and these two data sets could be slightly less correlated. And then if I continue this operation, if I calculate a mean value here and a mean value here, and these data sets will be even more less correlated. So by doing this blocking operation over and over, you can see that certain time scale, at certain block length, you will see some completely uncorrelated data set, and that's what we want to do. So once you understand this blocking operation, what we will do is, we will go to each block and then calculate mean value of A, and this B suffix here refers to an index for the block. So here we go from 1 to the tau B, and then we calculate the mean value. So what this mean value basically means is, in this particular block, you might have 3 data set, I plus 1 and I plus 2. So in this case, we are going to average over these 3, and that is what is given as mean value of A at that particular block. Okay, so this is basically going from 1, 2, 3, and then we sum, then we divide by 3. So that will give us one mean value for this particular block. So we'll have A at I, and similarly A at, so I'll put some B here. So you can see for each of these blocks, we can get the mean value based on the small segment. So then what we do is, and then for a given blocking operation, there will be NB number of mean values. That means if I go to this particular block, I already noted that based on the length of the segment, the number of blocks would be total run divided by the block size. So we are going to have the mean values for each of these blocks. So suppose if I have 10 such blocks, I'll have 10 such mean values for this particular blocking operation. So now what we can do is, we can actually calculate the variance in the mean based on these NB number of blocks. So that is the expression for this. Okay, so the mean value is for each block is known, and then this is the overall mean which we use for all the data, which is going to be anyway constant, and then we can get the variance in the mean. And now if you continue to do this, if the block size is more than the correlation time, and we do not know what is the correlation time yet, but there will be some time tau b which would be higher than the correlation time. As I noted before, the segment length goes from 1 to tau run. So the range of tau b that we are sampling is 1 to tau run, and our tau c is going to be somewhere in this limit. So in certain blocking operation, somewhere we would have reached this particular condition, that tau b would be, the tau b is nothing but the segment length of a block, and that would be more than the correlation time at some point of time. So when that happens, you will see that the way we calculate this variance of this mean will be proportional to 1 by, or the inversely proportional to the tau b. So with this insight, what we can do is, we can calculate or define a quantity called statistical inefficiency S by taking this term here, okay, and then multiplying tau b sigma square of mean A, and then bring this down, you get sigma square A. And especially what we are trying to do is, we rearrange this equation to solve for tau c. So that would be tau b sigma square. So since we do not know what is tau c is, we put some dummy variable S and call it as a statistical inefficiency. And then when we continue this blocking operation, at certain tau b value, what will happen is, this S will become constant, and that's where we know that the data sets become completely uncorrelated. and this estimate for S, the plateau value at which this becomes constant, we will take that as a value of statistical inefficiency. So, this can be shown in this particular plot. So, we define this statistical inefficiency S, and then we plot. So, this can be plotted against tau b, but in this case it is plotted as a square root of tau b. Okay, it can be done with respect to tau b itself. So, what we have done is we are choosing different tau b values, that is, as I said before, tau b is 1 here, 2 here, 3 here, etc., etc. So, as you go to each of these blocking operation, we calculate the statistical inefficiency S for each of those blocking operation, because for each of those blocking operation we can calculate the sigma square AB and tau b is known, and then you plot this statistical inefficiency. As you can see that as tau b increases, the data set also shows an increase, and then it kind of reaches a plateau value somewhere here, and we consider this as the statistical inefficiency for this particular data set. For any other data set, you could do something similar. You do this blocking operation, and then you define the statistical inefficiency, and then look for this kind of a plateau value, and that is the segment length at which your data set becomes uncorrelated. In this particular example, we find that the plateau value reaches at S equal to 22, and what is the meaning of this 22 here is that in this particular data set, one data point in every 22 consecutive data set has new information. That means only after every 22 steps you get statistically uncorrelated data sets. Okay, so that should be your correlation time. So now the way we use such an information is, again going back to our expression here, the tau c that we have calculated is nothing but S here. Okay, so that we consider as 22 here. In this example, let's say you have some 30,000 data points, and in that 30,000 data points, in this example, only 1 in every 22 data points have new information, or they are not correlated. And then let's say sigma here is calculated over this 30,000 step as some 10.9 megapascal, let's say. So then the error in the mean calculation will be calculated from this expression, and then when you take the square root, sigma becomes sigma is equal to square root of Tc by tau n times sigma a. The sigma a here is based on all the 30,000 data, that is 10.9 megapascal, and then this tau c here is nothing but S, which is 22, and tau run here is nothing but 30,000, and then when you substitute all these things, you can find the error in the mean is 0.42 megapascal. So for this particular data set, you would write the measured pressure is equal to some average pressure. So this can be calculated from the run average, and then the error in this mean. So the what is the expected error in this particular mean is given by 0.42 megapascal plus or minus. So any simulation data should be represented by this kind of expression with the mean value and the corresponding error in the mean value, and that has to be calculated based on the total simulation length and the corresponding autocorrelation function. Sorry, the correlation time. To get the correlation time, we define something called statistical inefficiency, and then based on the blocking operation, and from here we find the correlation time. So now to go back, so initially we had the sigma square A run as sigma square A divided by tau run. This is true only if all the data set in this tau run data points are statistically independent, but in MD simulation there could be some correlation of the subsequent data set, because we do not know a priori what is the correlation time. And suppose if I know what is the correlation time, we can correct this formula and then we use this, where the total number of data set is actually normalized with respect to the correlation time. Now we discussed there are two ways in which we can get the correlation time. Once we know the correlation time, we can use this formula. The first thing is to get the correlation time and get the autocorrelation function CAA, and then from there you get the correlation time. That's one approach. The other approach is you take the total data set and make them into segments of various lengths, and then you find out at what blocking operation the correlations are eliminated, and then you can find what is the effective number of data sets out of this total tau n data set. And that's what we have done in the second approach by doing this kind of blocking operation. And then we also show that how to use this formula once we know the correlation time and the total number of simulation points and the sigma square A based on the total number of simulation points. Now generally when students write error bars, generally they report this value as the error, and that is not correct, because this error in the mean depends inversely proportional to the number of data sets it has to be from this particular formula, either this formula or this formula, and you would report the final data as some mean plus or minus some error in the mean. So to summarize, we learned that at equilibrium, thermodynamic properties will have a Gaussian distribution, and then we discussed there are two possible errors in MD simulations. One is a systematic error that comes from the way we have designed our simulations, choices of the parameters and methods, system size, etc. The other one is a statistical error that comes from how long we do the simulations, how many data set we use to calculate the errors, and in calculating statistical error, we need to find out what is the correlation time for that particular property, which could be either explicitly calculated in a pre-simulation, or it could be found out by defining the statistical inefficiency at a blocking operation, and once you get a correlation time, then we can obtain the error in the mean calculation.